Okay, perfect. All right. Okay, so welcome everyone to this new edition of the Flow seminar. So I'm Aurélien, I'm one of the co-organizers of the seminar with Peter, Virginia, Dan, Samuel, and Sebastian. So for newcomers, so this Flow seminar is here to provide a forum to discuss the latest scientific results in federated learning, trying to cover many aspects ranging from distributed optimization, learning theory, privacy, like today's talk, security, communication compression, also things related to systems, hardware, and applications. So before I introduce today's speaker, maybe just a brief recap of how to ask questions. So you can do that during the talk, but all the mics are off by default. So you should just use the raise hand feature or ask your question in the chat. And yes, then we can essentially unmute you. So you can ask the question yourself. So feel free to ask questions during the talk. All right, so our speaker today is Samuel Maddock. Thanks a lot for accepting our invite. Samuel is a PhD student in computer science at the University of Warwick, where he previously completed a master's in discrete math. His research interests lie at the intersection of privacy and machine learning, with a focus on federated learning, which is great. Seems great flow. And today he will be talking about privacy auditing for federated learning. So where the goal is to try to complement formal differential privacy guarantees, which can in many cases be quite conservative, with more empirical privacy measures that consider more realistic threat models. So thanks again, Samuel, and the floor is yours.
Thanks so much for that intro, Aurélien, and yeah, thanks for having me. I'm excited to be here. So yeah, today I'm going to be talking about our recent work, crafting Canaries for empirical privacy measurement in federated learning. And this is joint work with Alexander Sablerol and Pierre Stock at Meta AI, and it's just recently been accepted to ICLR. So I guess to get right into it, as Aurélien mentioned, our work is focused on providing empirical privacy measurements for federated learning. So I guess it helps to start with what is federated learning, which I'm sure I don't really need to explain to this audience in much detail, but I think it's always good to kind of be on the same page. So, you know, FL has been recently become a really popular paradigm for distributed training of machine learning models. And the key idea, of course, is to move computations on device so that the participating clients never have to share their raw data, which might be private. And instead, a server kind of orchestrates training by sending the participating clients the current model at around, and the clients themselves will perform a number of local, for example, local SGD steps for sending back a corresponding model update to the server. Now, because the clients themselves don't kind of share raw data, there's often this misnomer that federated learning provides privacy by default or by design. But there's been a number of recent works that show that actually these model updates that clients send do leak information, and they allow adversaries to perform a number of sophisticated attacks. For example, membership inference, or even reconstruction attacks of the actual raw samples themselves that are used in training. So because of this, the kind of de facto approach to preventing such leakage is to rely on the formal notion of differential privacy. Now, I don't want to dwell on this definition too much. It's not really too important here. But I guess the most important thing to know when you're working with differential privacy is that the differentially private algorithms are parameterized by an epsilon and a delta. So the epsilon is often referred to as the privacy budget, where a larger epsilon often implies less privacy. And delta here is this kind of small probability of failure that you fail to guarantee differential privacy, and it's usually set to be very small. Now, the main advantages of differential privacy is that it has a lot of attractive properties that can be used to build private algorithms in a kind of like building block type approach. So we have nice properties such as post-processing, where if you release something under differential privacy, you can kind of do anything with the output and it still remains differentially private. Of course, we also have things like composition, which kind of informally says that if you release lots of things that are individually differentially private on the same data set, then their privacy parameters essentially add up and kind of compose nicely in some way, which tells us about the overall privacy of their combined output. However, as is kind of often the case, proving theoretical guarantees can be challenging kind of in practice. So one of the most important examples of this, I suppose, is the analysis of DPSGD, which is used to train machine learning models. And I guess I should say that it's not actually that difficult to prove that an algorithm satisfies differential privacy, but it can be very challenging to come up with analytical expressions or ways to find the kind of tightest privacy bound possible, so the tightest epsilon. Right, and if we remember here that kind of large epsilons mean less privacy, then we would really like to show the tightest epsilon possible. So there is often this kind of inherent looseness in a lot of the analysis in methods like DPSGD. Of course, we're talking about federated learning, and so a common method to prevent such privacy leakage in federated learning is to combine differential privacy with a standard FL type approach. And so the standard method for doing so is based off of DP Fed averaging. So I'm kind of presenting a somewhat abstract version of this here. So if we kind of remember in federated learning, all clients receive a global model at a particular round, and they do some amount of local work. So for example, they take a number of local SGD steps on their data sets. And then from this, they produce model updates, which are essentially the difference between the current global model and their newly updated local model. Now, in order to guarantee differential privacy, these model updates can be clipped by the clients and then sent to the server, which are then aggregated and Gaussian noise is added with sufficient variance to provide formal differential privacy guarantees. Now, in practice, the adversaries, if there was an adversary listening in, we want to prevent them from seeing the individual clipped updates. So typically you apply some form of cryptographic techniques to do this aggregation. Now, as is often the case in differential privacy, there is this tension between privacy and utility. So as I mentioned, differentially private algorithms, they're parameterized by the privacy budget epsilon. And in order to guarantee small epsilon, we often have to add more noise. And so recent work has shown that, particularly in the central setting of differential privacy, there can be gaps between the theoretical epsilon that we can kind of prove a model has been trained to and an empirical epsilon. And this kind of leads directly into some kind of problems with differential privacy in practice. So I guess in general, differential privacy is a very conservative measure. It's a worst case privacy measure that depends on kind of very adversarial scenarios, and it has quite a strict threat model. So there are a lot of challenges with using differential privacy in practice, especially in machine learning, and even more so with federated learning, where even without privacy, federated training is usually harder than training in the central setting. And so when you add in differential privacy, you add in noise, it gets even more difficult. So a lot of recent work has shown that you really get quite a significant loss in model utility, even with relatively large privacy budgets. For example, epsilons of the range of 20, 30, so on. And a lot of recent work has also shown that there is kind of vacuous information leakage guarantees in practice, and that also the information that can be recovered by empirical attacks is often less than what's predicted by the differential privacy bound. So this leads...
Oh, sorry, maybe just a quick question here.
Yeah.
Perhaps I'm not sure I understood what you mean here by vacuous information leakage guarantee. This seems like epsilon equal 20 is essentially saying that, right? But
yes, yeah. So I guess what I mean by this is more so the second point is that actually what you can recover in practice is often less than what's predicted by differential privacy.
Right. Okay.
By the theoretical epsilon. Yeah.
Thanks.
So this kind of leads me directly into kind of our work. So the aim of our work really is to design an attack to measure empirical privacy of DPFL pipelines under realistic assumptions. So ultimately what we want is to compare theoretical epsilon with what a strong adversary can achieve. And try to come up with this empirical epsilon that's kind of directly comparable. And why do we want to do this? Well, I've kind of mentioned that some central attacks have shown gaps between theoretical and empirical epsilons, but typically these methods are not that applicable or realistic for federated scenarios. So they often assume that the adversary has a lot of knowledge, typically about other samples in the data set, or they might require multiple models to be retrained in order to obtain this empirical epsilon measure. And so we're interested in designing a kind of more practical attack that's well suited to the federated setting. And how do we do this? Well, our idea is based on designing canary samples. So canaries are typically samples that are referred to for probing memorization, often in large language models. And they're typically handcrafted. So they could be, for example, a prompt that says, my social security number is, and you're interested in prompting the model to release private information that it might have memorized during training. Now, in contrast, in our work, we're interested in proposing an optimization scheme for designing canaries with a very specific property. And so this optimization procedure can be done, for example, by a server to simulate a strong adversary. And this will allow us to kind of get this empirical privacy measure. And the whole point of this optimization scheme is to produce a canary sample that's kind of sufficiently out of distribution to allow for a worst case privacy measure. So this brings us directly to our work, which is canaries in federated environments, or CANIF for short, that kind of operates in this following setup, which is a fairly standard federated scenario. So we assume a standard DPFL training pipeline where we have an honest but curious server who sends a model to each of the participating clients at a round. And we assume now also the presence of an adversary who is listening in on the model training. And they may choose whether or not to participate. And the adversary's goal is to craft this out of distribution sample, which is the canary. Now, a key assumption that we're also making here is that the row client has no direct access to model updates or gradients. So they must produce a real training sample. And once this canary has been designed and the model update has essentially been poisoned via this canary sample, the adversary can detect whether or not the canary was present in the current global update. And the whole point of this procedure in practice is, as I mentioned before, to allow a server or the central aggregator to emulate this adversary and that represents that holds a sample that represents a worst case kind of privacy leak. So the server can kind of perform these steps as a membership inference attack to measure privacy. Okay, so I think it's worth explaining in a bit more detail about the general kind of threat model that we're assuming in our CANIF work. So as I just mentioned, CANIF's focus is on a membership inference game. And we also assume a kind of an honest but curious server, which is in contrast to a lot of previous FL attacks that are also based on kind of model poisoning. We're also assuming here that the adversary is this row client that holds this outlier sample. And the whole membership inference game is that they're trying to infer the presence of this sample in the aggregated noisy model update. So one key assumption that we make that's quite important is that we don't allow the adversary to tamper directly with model updates. So in practice, this could be enforced by things like secure sandboxing schemes where the clients only input the samples into the local training process, and then they have no direct way to tamper with gradients or model updates. As the adversary can't modify gradients or model updates, instead they must produce a real training sample. And this is kind of good from a privacy perspective because it represents designing like the most out of distribution or adversarial sample from purely a privacy perspective. We also assume that the adversary doesn't know the exact model updates in the round. And so this is actually unlike some of the attacks in the central setting that often assume the adversary has kind of significantly more knowledge kind of about what's going on in the training process. But because of this, we have to assume instead that the adversary knows an approximate data distribution. And this is what we call the design pool. So the adversary will have to craft their canary on this design pool, hoping that it's a reasonable proxy for the federated data distribution. And this might seem like possibly quite a strong assumption, but we actually find in practice you often only need to know the task of your machine learning model in order to choose a good design pool, for example. So you could perhaps craft this design pool from public data sets and then use this to design your canary. And finally, also, like in our experiments, we assume the adversary knows kind of a calibrated threshold for the attack. So it can kind of maximize accuracy or minimize false positive rates, whatever metric it wants, so that it's kind of conservative in this way. Okay, so this kind of brings me directly to how do we start designing these canary samples, and what properties do we want from an out-of-distribution canary, essentially. So it helped to look back at the noisy aggregated update, which is formed from the sum of clipped model updates that are sent from the clients, and of course the Gaussian noise that is added to guarantee differential privacy. And I claim what we really want is for the Canaries model update to be orthogonal to all of the other updates at the current round. And I'll explain more why in a moment, but essentially why we want this is that it will lead to a separation of two Gaussians. So it's kind of very classical membership inference type game. And so if the design goes very well and we achieve this property, we'll be left with this with the problem of separating two Gaussians, depending on whether or not the canary was included in the current round or not. And then what we want to do is we want to kind of repeat this attack multiple times to form membership histograms, to form multiple attack scores where the canary was present or not. And then this will allow us to calculate any number of metrics from the attack, such as the false positive and false negative rates. And this can directly lead to an empirical epsilon measure that I'll talk about again in a moment. So as a kind of illustrative example here, you may have a real data sample like on the left, and we can see that this sample cannot be easily separated from whether or not it participated in the current round or not. But after our canary design procedure, you might end up with something that looks like, essentially here, random noise, but has this very specific property that allows for separation between whether or not this canary sample was included in the round or not. And therefore, in this case, allows the attack to succeed very well. Okay, so in a bit more detail, I mentioned that the rogue client itself is producing an outlier model update, but it's doing this through a canary sample because it can't directly manipulate gradients or model updates. So the key assumption that we make is that the adversary holds only a single sample, which is the canary, and therefore its model update is going to be proportional to something like the gradient of the canary. And so the desirable property that we really want is for the canary's gradient to be orthogonal to every other model update in the round, which means here we want the dot product between them to be 0. So if this property holds, and we take the dot product between the noisy model update that the server has at the round and the canary update, then we're essentially going to get something that's basically two Gaussian distributions. So when the canary is not present in the update, all of these dot products in the first term are going to be 0 if the canary has been designed properly, because it's orthogonal to all of the other updates. And in the case where the canary is present, we're essentially going to get something that's Gaussian distributed, but centered at the square norm of the canary gradient. And therefore we can, oh, yeah, go ahead.
Oh, sorry, yeah, just a clarification here.
Yeah, sure.
I guess I'm a bit confused. So do you assume that you observe the individual updates, the noisy ones, or only the aggregation here?
So here we assume only the aggregation, yeah. So we're assuming that all you can observe is the noisy aggregated model update, which is this utility. Yeah. Okay,
and you try to make this.
And so what we're crafting is a canary sample that produces this canary update through the sample, and we're interested in calculating this dot product, which is essentially our kind of attack score. And so if the canary isn't present in the noisy aggregated update, we're going to get something that's Gaussian distributed and centered at 0. And if it is present, then we're going to get something centered on the square norm of the canary gradient. And it's also Gaussian distributed as well.
Right, because you said your canary, you want its gradient to be kind of orthogonal to each of the model model updates. So here you meant. So sorry,
yeah. So orthogonal to it can be orthogonal to each of the individual updates or the sum of the updates. It doesn't matter here really.
Okay, it's not equivalent though, but I guess it could be orthogonal to the global update without necessarily being orthogonal to each individual ones, right?
So we want it to be orthogonal to the update without noise. So it is equivalent here, I think.
Okay.
So you can be orthogonal to the sum of them or the individuals. Essentially, here it doesn't matter. I don't think. Okay, cool. Yeah, so I hope that's clear. So this kind of idea leads us directly into kind of an algorithm to try to achieve this property. As I mentioned, so I think this is kind of related to the question that you just brought up, Aurelian, that in the scenario that I've just mentioned, we want the canary update to be orthogonal to the individual model updates, but the adversary doesn't know these individual updates because they're going to be aggregated often via things like secure aggregation. So instead, what we assume is that the adversary has access to a design pool, which is essentially going to be a proxy dataset from which we can form model updates from. So essentially what we assume is that the adversary has access to this dataset and that they will form clients in some way that allows us to produce mock model updates, essentially.
Okay, indeed, this is okay. This clarifies my confusion. Thanks.
Yeah, so essentially we're going to simulate a bunch of mock clients and have them perform a number of local updates, form their model updates, and use this to directly design our canary. So this is the first assumption that we need. And then once we have these model updates, we can begin with a kind of optimization procedure to directly construct our canary sample. So to do this, we're interested in kind of constructing this loss function, which is essentially going to be composed of two terms. The first term is going to, we're going to try to minimize the dot product between the individual mock updates and the canary gradient. And we're interested in minimizing this so that the canary gradient will become orthogonal to the individual model updates. And we also have a second term here, which is to enforce that the canary gradient has sufficient norm. So it's important for two main reasons. The first is to prevent, I guess, like optimization collapse. So we need to make sure that the gradient is non-zero. And second of all, in differential privacy in DP Fed averaging, we're going to have a clipping constant. So all of the model updates are going to be clipped to some constant C. And we're interested in making sure that the canary gradient has this maximal norm possible to ensure that there's kind of the best chance of separation between our two Gaussian histograms. Now, recall that we're interested in directly producing a canary sample and not just a model update or gradients. And so because of this, we need to actually update our canary sample in some way. And so to do this, we're going to basically kind of backpropagate through this loss function and calculate a gradient with respect to the canary sample. And then we can directly update the canary sample via an SGD step. So this is quite straightforward for continuous data. So if you have image data, it's fairly straightforward. It's a little bit more complicated for natural language problems where often you're going to be backpropagating into a discrete space, which is your token space. But there is kind of some additional machinery that can be used to allow you to do this and still kind of update the canary sample in this gradient-based way. So finally, once we kind of do this optimization procedure, hopefully we'll produce a canary sample that has the properties that we want. And then from this, we can compute an attack score. So this attack score is formed from the dot product of the noisy model update at the current round and the canary update, which is formed from doing local training with a single sample, that being the canary. Okay, so that's pretty much how we're interested in designing a canary sample. But at the end of the day, we're interested in measuring empirical privacy. And so the design procedure that I've just highlighted can be used to produce a single attack trial by forming a canary and then taking the dot product between the current round's noisy update and the canary update. Now, to compute our empirical epsilon, we essentially use some recent methodology that's been popularized by recent work that's based on characterizing the differential privacy guarantees based on false positive and false negative rates of an attack. But one area that kind of differs from prior work, particularly in the central setting, is that our attack is kind of membership inference at a particular federated round. So what we obtain is a per round measure of privacy that we need to compose over multiple federated steps. And then this will allow us to obtain this empirical epsilon that will allow us to directly compare to the theoretical epsilon that's used in differential privacy. So I guess how do we do this? Well, what we really desire is a set of attack scores in order to calculate the false positive and false negative rates. And this is a slight problem so far because our design procedure produces only a single canary sample. So you can only really calculate one or two scores from this sample. So what we propose is to essentially monitor privacy at a particular round and attack the model at regular intervals. So if you imagine here that we have the test accuracy of your model across federated training, what we can do at these regular intervals that I've highlighted is we can essentially freeze the current global model, use Canif to craft a single canary in the way that I've outlined before, and then run the attack over a number of frozen rounds where the participating clients will change, but the model itself will not. The model will be frozen. And so we can do this multiple times to accumulate these attack scores and then calculate the true positive and false positive rates from this. And once we have these, we can compute our per round empirical epsilon measure. And once we have a set of these measures, we're interested in composing them in a way that allows us to obtain an empirical epsilon that will be directly comparable to the theoretical epsilon that was used to train the model. So how do we do this? Well, essentially what we want to do is obtain our per round epsilons, as previously mentioned, and then directly convert them into an equivalent noise multiplier that we can kind of compose using the accounting framework of differential privacy. So the first step of this process is what I've just outlined, is essentially that we can attack the model at regular intervals, and to do so, we freeze the model, we design a single canary, and then we calculate multiple attack scores by letting the participants change at each round, but we don't update the model. And from these, we calculate false positive and false negatives, and we can compute our per round measure. To compute our per round measure, we do this at essentially a calibrated threshold. So we're actually interested in maximizing this per round epsilon across the different thresholds on the attack scores. Then what we can do is we can take these per round measures and we can convert them into an equivalent noise multiplier, which is essentially the noise you would need to add in order to guarantee the equivalent empirical per round epsilon. And once we have this noise multiplier, we can compose it under standard privacy accounting. So here we're using Renyi differential privacy with amplification by subsampling. So we can compose these per round noise multipliers to get our empirical epsilon that allows us to directly compare to the theoretical epsilon. Okay, so I'll stop briefly here and just open up to any questions if there are any. Okay, so I guess I'm interested now in talking about how we use this Knief framework in some of our experiments and what we're kind of interested in looking at. So I've described the core ideas behind Knief and this threat model and how we can design these kind of canary samples. And now I'm going to briefly walk through some of these experiments. So in our experiments, we're mainly interested in a few different things. The first is a quick sanity check of our method in a kind of in a federated setting that simulates the central setting, just to understand how effective our attack is in essentially the easiest setting. And so to do so, we simulate a federated setting where each client holds a single sample, and hopefully more will become clear in just a minute. The second thing that we're interested in is measuring the empirical privacy during actual training runs of these DPFL pipelines, which is, of course, one of the main purposes of our attack. And finally, what I'll present is kind of a brief overview of kind of an ablation study that we did that looks into the design canaries themselves to find out whether design is efficient. And what I mean by that is it practical for an adversary on limited computation devices to perform the design? And a related part here is whether the resulting canaries are stable. So can they be designed effectively on the design pool? So to answer all of these questions, we evaluate on both image and language benchmarks. So for our initial experiment in the central setting, we use an IID split of cipher 10 for the federated experiments. And for the federated experiments, we rely on leaf benchmarks, which provide nice non-IID splits of datasets for us in the federated setting. So we focus on one binary image classification task of celebrity faces, which is the Celeb A dataset. And we train two different models on this, ResNet 18 and a simple convolutional neural network. And we also look at two language tasks. One of these is sentiment classification on a Twitter dataset, and the other is a next character prediction task for Shakespeare. And so we're typically looking at models in the size of a few million parameters. Some are quite smaller, but generally models that are quite practical for federated learning. It's also worth mentioning here that we're also only focusing on a kind of DP-Fed averaging, and we're also applying amplification by subsampling. So only a small percentage of clients are going to be participating each round. And as I've been mentioning, there's also another important point, which is that of the design pool, right? So in order to design our canary, we need a design pool. And so what we do is we form mock clients for the canary design to be taken directly from test set of our data sets. So the model never sees the data that we're designing on, but it is somewhat representative of the task. So particularly in the leaf data sets, because the data is non-IID, it's the case that you're unlikely to see in the training set this particular data that's in the design pool. And so it somewhat mirrors the situation that could occur in practice where you as a server are orchestrating FL training, and you might know about the specific task of the model, and therefore you might be able to craft your design pool from, for example, public data, but you won't exactly know the data distribution, because that's often very unknown in federated settings. Okay, so the first thing I want to look at, as I've just mentioned, is a kind of central setting. So here we're interested in training a model on cipher 10, where every client will hold a single sample. So this essentially corresponds to the central setting, where the number of clients is equivalent to a central batch size, essentially. And here the number of clients that are participating per round is 64. And so what we do is we train two different cipher 10 models, one without privacy and one with privacy. And we perform our Knief attack, and we take 100 attack trials, and we plot the resulting membership histograms. So the histogram on the left is for a model without any privacy, and one on the right is for a model with privacy. So what we can see is essentially that, so actually, just to take a step back, in order to compute these attack scores, what we do is we freeze the model at one particular round of training. We design a single canary, and then we perform 100 mock rounds, where half of the canaries are inserted and half are not. And what we observe here is that the resulting estimate of sigma is actually fairly close to the true noise multiplier that's used, right? So on the left, we're using no noise, and our estimate is fairly close to 0. And on the right, our noise multiplier is roughly 0.42. And again, our estimate is quite tight. And so really, actually, there's like no gain in privacy in terms of our empirical measure versus what's actually being used. So furthermore, still remaining in this kind of central setting, we're also interested in looking at how the design pool affects things. So if we remember, because we're in this kind of central setting, the number of clients per round is going to be equivalent to varying the batch size in the central setting. And a lot of prior work has typically shown that the central setting, you typically get more privacy if your batch size is larger. So we're interested in varying the number of clients, which again corresponds to varying the batch size. And we're also interested in varying the design pool size. So I guess here you can think of the design pool size as varying the adversary strength. So we would think that it's plausible that if an adversary has more data that's fairly representative of the true training data, then it would be able to craft a strong attack or stronger attack. And so what we do is here is a kind of similar plot from before, where we attack a model without any privacy, and we plot the mean standard deviation of the histograms formed from the attack. And we do this where we vary the design pool size and also the number of clients as well. And so we observe two things that are actually very in line with previous work in the central setting, which is that the attack is more difficult when you have a larger number of clients. And we also observe that the design pool size does have an effect, but it's actually maybe not as significant as you would think. So here, on this specific example, really after about 500 samples, you're not really gaining any stronger of an attack, even if you had 4 times the amount of that data, which is, I guess, a good sign, because it means that we don't have to have too much data. As long as enough of it is somewhat representative of what's being used in practice, then we can still design canaries that will work. Okay, so we've seen how the attack behaves in the central setting, and now we look at extending this to a more practical federated setting. So here I'm picking one of the leaf data sets just as an example. And this one is the Cent140 dataset, which is Twitter sentiment classification. And what we do here is we train an LSTM model on Cent140 for 15 epochs. And we train it to a final epsilon of 50 under differential privacy. So a relatively large privacy budget. And we have 100 clients participate per round, which is, I think, equivalent in the setup to a very small kind of subsampling rate of, I think, 0.2% of the total clients. And what we do is we perform our Knief attack to compute our per round empirical privacy measure. So again, to do this, every 100 rounds of training, we freeze the model, we perform Knief design to produce one single canary, and then over 100 mock rounds, where the model is frozen, but the participants will change, we compute our attack scores using the canary, we form our membership histograms, and then we can compute our per round empirical epsilon alongside its 95% confidence intervals. And so this process produces our per round epsilon, empirical epsilon. We can compare this directly to the theoretical epsilon. So this is essentially the per round theoretical epsilon the model is guaranteeing when you ignore composition and also subsampling amplification. And so we can observe two things here. So the first, you can kind of note this very small pattern as you start to train the model. its empirical privacy measure is kind of increasing, and then it kind of stabilizes for the duration of training. And the second observation, of course, is that there is this large gap between our empirical measure and the theoretical per round epsilon. Furthermore, we can then take these per round measures and we can compound them across the full training runs. So again, here we're still on set 140, but now we're training 3 different models to different theoretical epsilons. So theoretical epsilon of 10, 30, and 50. And we perform our Canaries privacy monitoring for these models, where we compound the per round measures via the method that I've previously mentioned. And again, we can see this kind of clear gap between the theoretical and empirical epsilons. And so we can do this again for our different leaf datasets. And we can also compare the empirical epsilons between the datasets as well. So the general pattern is quite similar within the datasets, but they're quite different between the datasets. And actually the reason for this is because of the different subsampling rates that are being used in these tasks. Okay, so this brings me now, I guess, to the final part, which is our kind of ablation study. So something I mentioned is we're interested in looking at how practical the attack is. So one of the big things here is how much data is needed in the design pool for strong estimates, and also how many design iterations are needed. So if we remember, our canary is produced through this optimization procedure. We don't really want this to take too long because it can, because in practice, the server is going to be performing this. And also, if we're mocking an adversary, typically these adversaries are clients that have limited compute as well. So as the first example of this, here is a plot where we're training a simple convolutional neural network on the celebrity faces classification dataset without any privacy. And what we study here is, first of all, 2 canary initialization methods. So one is where we initialize the canary to be random noise. And the second is that we pick an image directly from our design pool. And at the same time, we're also varying the design pool size. So we can observe 2 main things here, as we did in the central setting, really. The first is that you don't need too much data in your design pool to design relatively strong canaries. So again, here you're seeing this diminishing impact quite quickly. Again, you only really need a few thousand samples to kind of achieve the good canary design. And also we observe that there's no significant difference between initialization strategies as well. So this is positive because we can just randomly initialize our canary. We don't need to worry so much about starting with a canary that actually looks like the data that's going to be used. Okay, and this brings me to the kind of next ablation, which is on how many design iterations are needed. So this kind of directly corresponds to the computation cost of designing the canary. So here I'm plotting the design iterations on the x-axis against the attack accuracy for a model without any privacy. And so the general pattern that we can see is that more iterations are good, but we do have a kind of diminishing impact as you increase the number of iterations. And in terms of a kind of quantitative measure of computation, we actually benchmarked some of the design process like on a laptop. So as an example, on the CelebA dataset, with the ResNet 18 model, which is kind of the heaviest task, our design optimization procedure just takes under 10 minutes. So this is very practical for a server that has a GPU, and it's also very plausible for clients who might have limited computation. And it also fits within the kind of expected time for a federated round as well. And then just to kind of conclude here with, we also present some results that show a strong correlation between model test accuracy and the attack accuracy of the attack. Here trained without privacy, and also a similar correlation for the per round epsilons. So that's just to say that there's obviously these kind of well-known connections between privacy and model memorization, and it's something that our attack kind of shows as well. So that brings me, I guess, to the end. So to conclude, really, we kind of proposed this Knief framework that helps complement DPFL training by considering a practical threat model with a relatively lightweight design procedure that allows for tight estimation of model exposure. Now, that's not to say that our work isn't entirely without limitations. So the first being that we do assume the assumption of this design pool in practice. And this might be seen somewhat as restrictive because typically in federated settings, you don't know too much about the overall data distribution that you're training your model on. But we do believe actually that as long as you have some proxy data set that's could be formed from a public data set that somewhat matches the task of your model, then this should actually be sufficient from what we've seen in our experiments to design canaries that will still give you a good estimation of the model exposure. The second assumption is the requirement of client participation in mock rounds. So the model has to be frozen for a number of rounds in order to kind of accumulate these attack scores that are needed to compute a per round empirical epsilon. And this is somewhat problematic because clients and servers in practice wouldn't necessarily want to waste extra communication rounds and also some computation. So it's also worth me mentioning that there's also been some very recent works that follow up in this area. So one of these is a recent paper that looks at a one-shot approach to measuring empirical privacy in federated learning by Gallant, Andrew, and some other folks at Google. And actually, their approach is kind of similar to ours. So they're interested in designing canaries. But instead of doing the optimization procedure, they're actually just going to form random canary updates and rely on properties of kind of high dimensional spaces, which basically will say that with high probability, it's likely to be these randomly initialized canary updates are going to be orthogonal to the other updates. And the other second work that's also very recent is that of Nasser et al., who kind of restudy this empirical privacy problem. And among some of the many interesting observations that they have, they propose a more practical two-model approach, which can also apply to the federated setting. So I guess this is all to say that there are a few interesting follow-up ideas out there that are somewhat based on using canaries to measure privacy, and that they all have slightly different assumptions that can kind of help get around perhaps some of the limitations of the Knief framework. So I think I'll end it here. So thanks for listening, and I'll be happy to take any questions.
Thanks a lot, Samuel, for the nice talk. So yeah, we have some time for questions, maybe from the audience. I can start. Maybe I have a few ones actually. So maybe the first one is just maybe if you could elaborate a bit. So I guess it was on slide 30 or 31 or something where you use, you transform the empirical epsilon for a round into a noise multiplier, and then you do kind of the accounting on that. So can you elaborate on why you do that rather than, let's say, maybe composing the epsilons themselves?
Of course, yeah. So the main reason we do this is, I guess you can directly compose the epsilons using, for example, basic composition of differential privacy. But we're interested here in, I guess, matching how the accounting is done for theoretical differential privacy. And so what is done in practice is you compose under this framework of linear differential privacy, which among many things gets you slightly tighter composition of your epsilons, and also can benefit from things like amplification by subsampling. So really what we're doing is kind of mimicking what's done in the theoretical accounting in order to get something that's comparable.
Yeah, makes sense. And maybe a second question, maybe just about the first part of the experiment. I'm not sure whether I understood really the setting correctly for the CIFAR 10. So here you show that there is no, essentially no gap or almost no gap with the theoretical guarantees. Is this because here you assume like more knowledge for that setup, or I guess, or is it because the model is simpler? I was a bit
Yeah, so I guess there are a couple of reasons. One, in some sense, we are assuming more knowledge in the sense that our design pool here, so the Sci-Fi 10 dataset is identically distributed. There's no non-IIDness. And so the way we form our design pool is basically from IID data. So what we design our canary on is actually very representative of what's used in the training. So that's the first thing. The second as well is that it's an easier setting in the sense that every client only holds a single sample, so that this directly corresponds to a central setting of differential privacy. And so the number of clients per round corresponds to a central batch size. And typically, if you have quite a small batch size, the membership inference attacks do often succeed with quite high probability. And so actually in this specific example, we're using 64 clients per round, which is, I guess, a relatively small batch size.
Okay. And in the federated cases, the design pool, so you said it's constructed from like test data, but
yes.
Can you be a bit more specific? Do you make clients? I mean, it depends a bit how the data is split in the first place, right? But you could make clients by picking IID data from this test set, or you could actually construct a set of clients that have non-IID data, right? So can you clarify?
Yeah, that's a great point. So we're directly using clients that have already been pre-split in these leaf benchmarks. And therefore the clients themselves, the mock clients, have local data sets that do exhibit non-IIDness.
All right. I have a few more questions, but maybe we can take questions from other people. Do people have questions? Again, you can raise hand or type in the chat. Okay, not so many questions. The talk was super clear, perhaps. Probably this auditing, privacy auditing things was also somewhat new to maybe many people. I think, given its fairly recent topic and especially in federated learning. Okay, so if you don't mind, I will ask a few more questions.
Of course.
So I'm wondering a bit. So in the end, so what is the lesson a bit, or what can we conclude from these results? So I mean, the results of your evaluation in federated learning settings show this gap, right, between theoretical privacy and empirical privacy, but perhaps it is not very clear, at least to me, whether we can attribute this. I mean, what can we attribute this gap to, right? There are many reasons. There is the fact, like you said, that maybe the adversary has access to, okay, it relies on a design pool that might be not very perfect. There is also the case that it's not worst case data, right? You use realistic data and then you craft just one worst case point, but in a way, right, the privacy can be better because the rest of the data is kind of normal data. It can be also from the algorithm dynamics, right? The fact that maybe, I don't know, doing federated learning, maybe with focal steps, or I don't know what exactly, leaks less across iterations than what composition, would give us or something. Yeah, can you comment a bit on whether, or yeah, I'm not sure whether more ablation study could be done.
Yes, yeah.
Try to disentangle this is probably not so easy, but
yeah, I mean, I think you make some really great points. Essentially, yeah, I think the way that you just outlined that essentially there are many places where there could be, I guess, error that's coming in that's causing this gap. One of these, as you pointed out, is the fact that you're designing your canary on this design pool that is going to be representative, but there's still going to be some error there, especially in a federated setting where you might not know too much about the data distribution. The second of all, of course, is that we're designing this canary through the optimization procedure. And so there is kind of inherent error that's coming through when you do this optimization procedure. So we didn't really observe it too much, but I guess because you're designing on this, on the design pool, it's possible that the canary you design maybe doesn't generalize so well to model updates that are actually going to occur in practice. But we didn't really observe this, but I think you are right that it would be interesting to, I suppose, perform more ablation studies to really look at what specifically is causing that gap with these types of approaches.
Okay, I was thinking also about maybe putting some constraints. So there's a related question, but maybe I guess it would be interesting also to see how much of this gap is due to generating some kind of worst case example where you don't put a particular type of constraint on the sample. You don't try to make it necessarily plausible or realistic.
Yes, yeah.
So it depends what you try to measure, but you could in some setting maybe you're interested in measuring the potential privacy leakage for plausible data, right? Maybe it's not an attack scenario of someone putting some completely out of distribution data. You just want yeah. I guess it's more of a follow-up potentially, but it would be interesting to see also how much comes from the sample being potentially completely rubbish as an image.
Yes, yeah. Yeah, so I think that's a really great point. Yeah, because we're not constraining the canary sample in any way. So you might produce something like this, which looks like random noise on the right here. And I think it would be interesting to study privacy where you constrain the adversary to have a canary that does look like real data in some way. Of course, that might be challenging to do, but I'm sure you could construct scenarios where you do study in this like ablation study type way to see how much of an effect this is having on the privacy measurement. Yeah.
Did you try just to use kind of the best real data points that you have in replacement for the canary? Like, does it completely destroy the attack if you do that? A bit like is suggested in this illustrative figure. But... Yeah,
so actually these histograms, so they're not exactly of these two images, but they are of a real image on the left and on a canary image on the right. So we didn't look specifically at choosing like the worst case sample in the dataset, but from what I observed, when you start with a real image and you turn it into a canary, a lot of the real image histograms will look like something on the left, where there is really no separation and it does destroy the attack.
Right, makes sense. Okay, I think I'm pretty much out of question now. So if there is no additional question from the audience, I don't see any raised hands. Yeah, we are right on time. So thanks again for the nice talk.